Hi guys, last time we saw the importance of the gate driver and gate resistor. This time we'll see what is a gate driver made of and how does it work. So let's start. The very basic driver IC can be shown like this. The working of these switches to provide charge to the MOSFET is mentioned in my previous video. These switches are turned on and off to provide the gate threshold voltage to the power device. These switches should be electronically controlled. So the basic electronic switch that we can use is a BJT because of their efficient area utilization and better performance. The BJTs are easily controlled inside the gate driver. Small signal is sufficient to turn them on. So we'll replace these two switches with NPN BJTs. We'll name them as Q1 and Q2. When we need to turn on the power MOSFET using a gate driver, then we need to provide the gate threshold voltage from the driver. So internally, this Q1 should turn on. When this BJT turns on, the current flows from the BJT Q1 and provides charge to the power device. And when we need to turn off the power switch, then this BJT Q2 should turn on and Q1 should turn off, so that the gate of the power device is connected to the ground, which will discharge the input capacitance during the turn off process. One very important thing we need to consider is that both of the BJTs Q1 and Q2 should not be turned on at the same time. If that happens, then the supply voltage will get shorted to the ground and this driver IC as well as the whole circuit will get compromised. Well, to switch these BJTs, we need to provide two different switching signals which will be different on and off signals. When one BJT gets on signal, then by default the second BJT should get off signal at the same time. But when we provide the PWM to the MOSFET, we provide only one signal to turn on the power device. Then how come this requirement will get fulfilled? To do that, we can provide two NOT gates like this. One NOT gate gives signal to the BJT Q1 and other NOT gate will provide the signal to Q2. NOT gate 1 and NOT gate 2 are connected in series. The output of first NOT gate goes to the Q2 and output of second NOT gate goes to Q1. So logically, BJT Q2 will get an inverted signal with respect to the input pulse and Q1 will get the same signal as that of input pulse after two inverted cycles. Now, when we provide a high pulse to turn on the MOSFET, then the first NOT gate will give a low pulse output to BJT Q2, hence it will be turned off. This low pulse will go to the second NOT gate and it will provide high pulse to the BJT Q1 and it will turn on. So when the high pulse comes from the input, the Q1 turns on and Q2 turns off by this logic circuit. The current flows from BJT Q1 and power MOSFET turns on. When there is a low pulse at the input of the driver, then the first NOT gate will provide high pulse to both BJT Q2 and second NOT gate. Q2 will turn on and output of the second NOT gate will be a low pulse, so the Q1 turns off. Hence, when a low pulse occurs at the input, the Q2 BJT turns on and Q1 turns off. This is how a small signal gets converted to a high powerful gate voltage, which can be as high as 20 volts depending upon the gate requirements of the power device. This configuration makes sure that both of these BJTs do not turn on at the same time. Well, the NPN transistors can handle currents in one direction only. The high side NPN can source but cannot sink the current, while the low side BJT can sink but can't source the current in this configuration. MOSFET switching sometimes causes the back current. We have seen about that in one of our previous videos. This backcurrent occurs due to transients in the MOSFET in the circuit. This flows to the intrinsic gate-to-drain capacitor of the MOSFET and tries to flow into the gate driver during the turn-on and turn-off event. But the BJTs don't allow that. This transient should be taken care of, or else it will damage the internal transistors of the driver. To mitigate and provide a path for these reverse currents, we can use a low forward voltage drop Schottky diodes for protection in anti-parallel configuration. The diodes must be placed very close to the output pin and to the bypass capacitor of the driver. The selection of this bypass capacitor is also very important. We need to keep in mind that these diodes protect the driver only. They are not clamping the gate to source voltage against excessive ringing, especially with the direct drive where the controller IC might be far away from the gate to source terminals of the MOSFET. When there will be any transients, this upper diode will sink the current to VDD. And that's how a driver IC can get protected by a transient pulse. Well, this is what a basic MOSFET gate driver IC is made of. There are some more features such as under voltage protection, over temperature detection, etc., which are also introduced in the gate driver IC to make it more efficient. Well, that's it for now. Next time we'll see how we can use these MOSFET drivers more efficiently in our circuits. Till then, stay tuned. I've added all the reference on this topic in the description. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.